Hello, welcome to my presentation video on energy efficiency in electrical distribution. My name is Martin Lavachka, and in this video I'm going to talk about energy efficiency in brief, energy efficiency in electricity, diagnostics through electrical measurement, energy saving opportunities, and how to evaluate energy savings. World energy consumption continues to grow with no perspective of slowing down shortly. This trend is driven by different factors, both economic and sociological. An increase in the world population, particularly in countries where the energy use per person is expected to grow in the future. For example, today over 1 billion people have no access to electricity, and around 40% of the world's population is living under water stress. This means that energy needs will be increased in the future to allow people to benefit from a better standard of living. This additional energy need is globally not compensated by a decrease in energy consumption in developed countries. According to the International Energy Agency, the average energy use per person is increased by 10% between 1990 and 2008. Urbanization and industrialization, particularly in developing countries. This means that more energy will be needed for construction, manufacturing, and transportation of people and goods. The major part of energy is today obtained by burning fossil fuels. The consequence of this is the emission of huge quantities of CO2, which has an accepted impact on climate change by the greenhouse effect. In addition, these fossil fuels are subject to fluctuation in prices because of geopolitical issues and competition between countries. For these reasons, there is a global commitment of countries to curb the use of fossil fuels. The Kyoto Protocol was the first international agreement by which industrialized countries set objectives to reduce greenhouse gas emissions. Such a commitment was confirmed during the Conference of Parties in 2015 to limit global warming within acceptable limits. To reach these objectives, different regulations have already been put in place in many countries, relative to energy efficient construction, for example. One of the solutions proposed to solve the dilemma between economic development and CO2 emissions is to increase the part of electricity in the energy mix. Production of electricity represents around 30% of fossil fuels consumed worldwide, and 68% of electricity is produced from the combustion of fossil fuels like coal, oil, and natural gas. So, action that must be taken should include development of the use of renewable energies. Unfortunately, cost is still an issue, particularly during periods when the price of fossil fuels is low. The other major issue is the fluctuating nature of solar and wind generation. Energy storage is needed, which can significantly increase the cost yet again. Energy efficiency. The objective is to provide the same level of service by consuming less energy. By implementing energy efficient electrical equipment and smart controls, it is possible to save up to 30% of energy. This is the most cost-effective means for limiting CO2 emissions and saving energy and costs. An international appetite for regulation. Energy efficiency in buildings can be the result of regularity measures. With the evolution of regulations and directives can be issued at national or international levels, or voluntary approach with green building certification systems such as LEED, BREEAM, etc. Promoters, building owners, occupiers, etc. may decide to have their building certified to help adopt sustainable solutions and to obtain market recognition of their achievements. Energy efficiency regulations in Europe. Europe has issued two directives that emphasize the need for improvement in energy efficiency. Energy Efficiency Directive. The 2012 Energy Efficiency Directive establishes a set of binding measures to help the EU reach its 20% energy efficiency target by 2020. Under the directive, all EU countries are required to use energy more efficiently at all stages of the energy chain, from its production to its final consumption. In particular, any company with more than 250 employees has either to regularly perform an energy audit or has to put in place a permanently installed energy management system. Directive requirements are minimum requirements and shall not prevent any member state from maintaining or introducing more stringent measures. Energy Performance of Building Directive. This directive came into force on 4 January 2006 and lays down energy performance requirements such as all new buildings should be near zero energy by 31 December 2020. Energy performance certificates are to be included in all advertisements for the sale or rental of buildings. EU countries must establish inspection schemes for heating and air conditioning systems or put in place measures with equivalent effect. EU countries must set minimum energy performance requirements for new buildings, for the major renovation of buildings, and the replacement or retrofit of building elements. EN 15232 standard applies for building management systems and building automation and control systems. Many countries have issued green building certification systems for energy efficiency, cost allocation, and optimization. Some of them are listed as examples in figure K3. Energy efficiency standard. It is important to differentiate standards that apply to a complete site assessment from standards that apply to measurement devices used to help site assessments, as shown in figure K4. ISO 50001 is the main international standard providing requirements on energy management systems. It provides a framework of requirements for organizations to develop a policy for more efficient use of energy, fix targets and objectives to meet the policy, use data to better understand and make decisions about energy use, measure the results, review how well the policy works, and continually improve energy management. ISO 50006 is a companion standard of ISO 5001, providing practical guidance on how to monitor energy efficiency with the help of energy performance indicators measured on periods. Comparing energy performance indicators between the baseline period and the reporting period means measuring energy efficiency improvements. One element highlighted in ISO 50006 is the importance of defining and quantifying the factors or variables that may have an impact on energy consumption to compare energy performance under equivalent conditions. In the context of international regulation on energy efficiency, the IEC 60364-8-1 standard has been developed specifically for electrical installations. The standard gives requirements and recommendations for the design of an electrical installation with an energy efficiency approach. This emphasizes the importance of energy efficiency in the design of electrical installations, in the same way as safety and implementation rules. In the manufacturing industry, energy efficiency can easily be defined by the quantity of energy necessary to manufacture one product. For an electrical installation in a building particularly, energy efficiency is defined as a system approach whose objective is to optimize the use of electricity. This includes minimize energy losses, use electricity at the right time and lower cost, and maintain the performance all along the installation lifecycle. Here are the main points to keep in mind while implementing an energy efficiency approach in an electrical installation. There must be no conflict with the requirements relative to the safety of people and property. There must be no deterioration of electrical energy availability. It applies to new and existing installations. It can be implemented anytime, the only point of consideration being the rhythm of investment. And this is an iterative approach and improvements can be incremental. The ROI is the decision factor for the implementation of new equipment dedicated to energy efficiency. Technical guidance is provided on the design principles, taking into account the following aspects: optimal location of the high voltage low voltage substation and switchboard by using the barycenter method, reduction of the wiring losses by increasing the CSA of cables and by implementation of power factor correction and harmonic mitigation, determination of meshes or zones with equipment having similar energy requirements, load management techniques, and installation of control and monitoring equipment. An example of an assessment method is given with 5 levels of performance considering different aspects such as monitoring of load profile, location and efficiency of the transformer substation, and optimization of motor, lighting, and HVAC equipment efficiency. For example, figure K8 gives the recommended assessment levels for the determination of load profile and kilowatt hour. Other assessment levels are defined and specified per type of activity: residential, commercial, industrial, or infrastructure. It is important to note that the objective of energy efficiency is not only making energy savings. Implementation of energy efficiency must keep the same level of service and safety and maintain performance while saving energy and money at present and in the future. Figure K9 from IEC 60364-8-1 illustrates how to implement the electrical energy management system within the installation. Step 1. The inputs from the user shall be taken into account, such as the building temperature set point. Step 2. All sources of energy are considered based on availability and real-time price. Step 3. Inputs from environmental data are taken into account to avoid inappropriate decisions such as switching on the light during the day. Step 4. Inputs from the load are extracted as they are key to verify the accuracy of the load profile. Step 5. Detailed information on energy consumption is provided to the user. Step 6. Decisions are taken relative to the loads such as load shedding. Step 7. Decisions are taken relative to the sources of energy to deliver the service to the user at the lowest cost. Whilst it is currently possible to obtain energy savings of up to 30%, this potential reduction can only really be understood in terms of the differences that exist between active and passive forms of energy efficiency. Passive energy efficiency is achieved by such measures as reducing heat loss and using equipment that requires little energy. Active energy efficiency is achieved by putting in place an infrastructure for measuring, monitoring, and controlling energy use to make lasting changes. Savings from 5% to 15% may be easily obtained by the implementation of passive energy efficiency. Typical measures include decommissioning redundant systems, use of high efficiency motors and lighting, and power factor correction. More significant savings can be achieved by the implementation of active energy efficiency measures, typically up to 40% on energy for motors by using control and automation mechanisms to manage motorized systems, and up to 30% on lighting by introducing an automatic management mechanism based on optimal use. Active energy efficiency does not require highly energy efficient devices and equipment to be already installed, as the approach can be applied to all types of equipment. Good management is essential for maximum efficiency. There is no point in having low consumption bulbs if you are going to waste energy by leaving them switched on in empty rooms. It is important to remember, however, that savings may be lost through unplanned or unmanaged downtime affecting equipment and processes, a lack of automation, adjustment mechanisms, or a failure to ensure that energy saving measures are adopted at all times. In addition, when the operator's electrical network is expected to undergo frequent changes given the activities in which it is involved, these changes should prompt a search for immediate and significant optimization measures. Approaches to energy efficiency also need to take other parameters into account, since assuming energy is transformed without any losses, the energy consumed by a piece of equipment may exceed the useful energy it produces. One example of this is a motor which converts part of the energy it consumes in the heat in addition to mechanical energy. Diagnostics through electrical measurements. The first step in an energy efficiency approach is to establish a diagnosis and primarily aims to get a better idea of where and how energy is being consumed. This requires the development of initial measures and a comparative assessment process to evaluate performance, defining the main areas for improvement and estimating achievable energy saving levels. The logic behind this approach is based on the realization that you can only improve what you can measure. With a large scope and detailed list of requirements, IEC 61557-12 applies to measuring devices addressing most applications in switchboards and panels worldwide. Standalone power measurement devices are the natural solution for obtaining relevant data at the most important points in the electrical installation. A large range of devices is available from manufacturers, covering the full range of voltage and current, providing data about a large number of different electrical quantities, with local display or remote communication capabilities. However, many advantages can be gained by combining the functions of measurement and protection in one single device. Firstly, this approach leads to a reduction in equipment installation costs. Installing one single device costs less than installing two. Combining these two functions in the same unit ensures the right sizing of current sensors, eliminates risks of connection errors, and guarantees correct operation with the whole unit tested in the factory. French standard AFNOR, published in November 2015 and described hereafter, is currently the most advanced document about concrete ways to build a measurement plan. The document proposes three levels of achievement: base level, medium level, and advanced level. Tables in Annex F of this standard define the appropriate measurement required to achieve each level of achievement of the measurement system. Measurement of active energy needs to be achieved zone by zone or mesh by mesh. Attention should be put on measurement by usage that can be helpful to determine potential sources of energy efficiency improvements. ISO 50006 provides guidance on energy baseline and on energy performance indicators. These items are mixing energy measurement with other relevant parameters, for example, measurement of energy consumption correlated with degree day or energy consumption related to the number of persons present within the plant, or other influencing parameters. All these relevant parameters need to be measured, estimated, or transferred from another database. It is also important to monitor the electrical distribution system, because some measurements can reveal some issues with energy efficiency and additionally some risks related to assets. Energy saving opportunities. Several different measures can be adopted to save energy. Reduce energy use. These measures try to achieve the same results by consuming less or reducing energy consumption by taking care to use no more energy than is strictly necessary. Save energy. These measures reduce cost per unit rather than reducing the total amount of energy used. For example, daytime activities could be performed at night to take advantage of cheaper rates. Similarly, work could be scheduled to avoid peak hours and demand response programs. Or energy reliability. They not only contribute to operational effectiveness by avoiding production downtime, but also avoid the energy losses associated with frequent restarts and the additional work as associated with batches of spoiled products. Everyone immediately thinks of equipment for transforming energy when considering areas where saving can be made. Less obvious, perhaps, are the potential savings offered by the various control devices and programs associated with this type of equipment. Motors represent 80% of electrical energy consumption in the industry segment. Motorized systems are one of the potential areas where energy savings can be made. Many solutions exist to improve the energy efficiency of these motorized systems, as described in the following slides. Those wishing to improve passive energy efficiency often consider replacing motors as a starting point, especially if the existing motors are old and require reviving. This trend is reinforced by the determination of major countries to stop low efficiency motor sales soon. Based on the IEC 60034 30 standard definition of three efficiency classes, many countries have defined a plan to gradually force IE1 and IE2 motor cells to meet IE3 requirements. In the EU, for example, motors of less than 375 kilowatts had to be IE3 compliant by January 2015. There are two reasons for replacing an old motor. The first reason is to benefit from the advantages offered by new high-performance motors. Depending on their rated power, high-performance motors can improve operational efficiency by up to 10% compared to standard motors. By comparison, motors that have undergone rewinding see their efficiency reduced by 3% to 4% compared to the original motor. The second reason is to avoid oversizing. In the past, designers tended to install oversized motors to provide an adequate safety margin and eliminate the risk of failure even in conditions that were highly unlikely to occur. Studies show that at least one third of motors are oversized and operate at below 50% of their nominal load. However, oversized motors are more expensive and sometimes less efficient than correctly sized motors. Motors are at their most effective working point when operating between 30% and 100% of the rated load and are built to sustain short periods at 120% of their rated load. Efficiency declines rapidly when loads are below 30%. The power factor drops drastically when the motor does not work at full load, which can lead to charges being levied for reactive power. Knowing that energy costs account for over 97% of the life cycle cost of a motor, investing in a more expensive but more efficient motor can quickly be very profitable. However, before deciding whether to replace a motor, it is essential to consider the motor's remaining life cycle, to remember that the expense of replacing a motor, even if it's oversized, may not be justified if its load is very small or if it's only used infrequently. To ensure that the new motor's critical performance characteristics are equivalent to those of the existing motor. Other approaches are also possible to improve the energy efficiency of motors. Improving active energy efficiency by simply stopping motors when they no longer need to be running. This method may require improvements to be made in terms of automation, training or monitoring, and operator incentives may have to be offered. If an operator is not accountable for energy consumption, he or she may well forget to stop a motor at times when this is not required. Monitoring and correcting all the components in drive chains, starting with those on the larger motors, which may affect the overall efficiency. This may involve, for example, aligning shafts or couplings as required. An angular offset of 0.6 mm in a coupling can result in a power loss of as much as 8%. To ensure the best overall energy efficiency, the motor's control system must be chosen carefully depending on the motor's application. For a constant speed application, motor starters provide cheap, low energy consumption solutions. Three kinds of starters can be used depending on the system's constraints. Direct online starter, star delta starter to limit the inrush current provided that the load allows a starting torque of one-third of nominal torque, and soft starter when star delta starter is not suitable to perform a limited inrush current function and if soft braking is needed. Examples of constant speed applications are ventilation, water storage pumps, wastewater treatment steering units, conveyors, etc. When the application requires varying speeds, a variable speed drive provides a very efficient active solution as it adapts the speed of the motor to limit energy consumption. It competes favorably with conventional mechanical solutions like valves, dampers, and throttles, etc., used especially in pumps and fans, where their operating principle causes energy to be lost by blocking ducts while motors are operating at full speed. VSDs also offer improved control as well as reduced noise, transient effects, and vibration. Further advantages can be obtained by using these VSDs in conjunction with control devices tailored to meet individual requirements. As VSDs are costly devices that generate additional energy losses and can be a source of electrical disturbances, their usage should be limited to applications that intrinsically require variable speed or fine control functions. Examples of variable speed applications are hoisting, positioning in machine tools, closed loop control, centrifugal pumping, or ventilation, or booster pumps, etc. To handle loads that change depending on application requirements, starters, VSDs, or a combination of both with an appropriate control strategy should be considered to provide the most efficient and profitable overall solution. Examples of applications are HVAC for buildings, goods transport, water supply systems, etc. The method for starting or controlling a motor should always be based on a system-level analysis, considering several factors such as variable speed requirements, overall efficiency and cost, mechanical constraints, reliability, etc. Lighting can account for over 35% of energy consumption in buildings, depending on the types of activities carried out in them. Lighting control is one of the easiest ways to make substantial energy savings for a relatively small investment and is one of the most common energy saving measures. Lighting systems for commercial buildings are governed by standards, regulations, and building codes. Lighting not only needs to be functional, but must also meet occupational health and safety requirements and be fit for purpose. In many cases, office lighting is excessive and there is considerable scope for making passive energy savings. This can be achieved by replacing inefficient luminaries, by replacing obsolete lights with high performance, low consumption alternatives, and by installing electronic ballasts. These kinds of approaches are especially appropriate in areas where lighting is required constantly or for long periods and savings cannot be achieved by simply switching lights off. The time taken to recoup investments varies from case to case, but many projects require around 2 years. More efficient lights may be a possibility depending on the needs, type, and age of the lighting system. For example, new fluorescent lights are available, although ballasts also need to be replaced when lights are changed. New electronic ballasts are also available, offering significant energy savings compared to the earlier electromagnetic ballasts. For example, T8 lights with electronic ballasts use between 32% and 40% less electricity than T12 lights fitted with electromagnetic ballasts. However, electronic ballasts do have many points of attention compared with magnetic ballasts. Their operating frequency can introduce high frequency conducted and radiated disturbances which can interfere with power line communication devices. For example, adequate filters must be incorporated, and the supply current of standard devices is highly distorted, so that typical disturbances linked to harmonics are present, such as neutral current overload. Low harmonic emission devices are now available, which keep harmonic distortion to less than 20% of fundamental current, or even 5% for more sensitive facilities like hospitals. The LED technology offers significant prospects for progress, especially for smart control. LEDs are considered as the sustainable alternative solution to achieve energy savings objectives in the lighting sector. This is the first lighting technology suitable for all fields, providing great energy efficiency and smart management capability. Other types of lighting may be more appropriate, depending on the conditions involved. An assessment of lighting needs will focus on evaluating the activities performed and the required levels of illumination and color rendering. Many existing lighting systems were designed to provide more light than required. Designing a new system to closely fit lighting needs make it easier to calculate and ultimately achieve savings. Apart from the issue of savings, and without forgetting the importance of complying with the relevant standards and regulations, there are other advantages associated with retrofitting lighting systems. These include lower maintenance costs, the chance to make adjustments based on needs, greater visual comfort, and improved color rendering. A less common passive energy efficiency measure, but one which is worth considering in tandem with the use of lights fitted with ballast, is to replace the reflectors diverting light to areas where it is needed. Advances in materials and design have resulted in better quality reflectors which can be fitted to existing lights. These reflectors intensify useful light, so that fewer lights may be required in some cases. Energy can be saved without having to compromise on lighting quality. New high performance reflectors offer a spectral efficiency of over 90%. This means two lights can be replaced by a single light with potential savings of 50% or more in terms of the energy cost associated with lighting, and existing luminaires can be retrofitted by installing mirror type reflectors without having to adjust the distance between them. This has the advantage of simplifying the retrofitting process and reducing the work involved, with minimal changes made to the existing ceiling design. The passive energy saving measures mentioned so far leave further scope for making savings. Lighting control programs aim to give users the required levels of convenience and flexibility, whilst supporting active energy savings and cost reduction by switching lights off as soon as they are no longer needed. There are many technologies available with various degrees of sophistications, although the time taken to recoup investments is generally short at 6 to 12 months. A multitude of different devices are currently available too. These various technologies may be combined and can also be used to create a specific effect or atmosphere. For example, programmable lighting panels in meeting areas have many different light settings which can be changed at the flick of a switch. Timers to turn off light after a certain period has passed. These are best used in areas where the typical time spent or period of activity is clearly defined. Movement sensors to turn off lights when no movement has been detected for a certain period. These are particularly well suited to areas where the time spent or period of activity cannot be accurately predicted. Daylight harvesting sensors to control light near windows. When sufficient daylight is available, lights are turned off or switched to night light mode. Programmable clocks to switch lights on and off at predetermined times. Dimmable lights to provide a low level of illumination at off-peak periods. Voltage regulation, ballast, or special electronic devices to optimize energy consumption for lights. Or wireless remote control devices for simple and economical retrofitting of existing applications. Some of the lighting control systems currently available, such as those based on the KNX protocol, have the additional advantage of supporting integration into building management systems. They offer greater flexibility of management and centralized monitoring and provide more scope for energy savings by enabling lighting controls to be integrated into other systems. Certain systems enable energy savings of 30%, although efficiency levels will depend on the application involved and this must be chosen with some care. If this type of system is to produce results, the design and implementation stage must begin with an audit of energy consumption and a study of the lighting system to devise the best lighting solution and identify potential reductions in terms of both costs and energy consumption. If the energy distribution company imposes penalties for reactive power consumption, improving power factor correction is a typically passive energy saving measure. It takes immediate effect after implementation and does not require any changes to procedures or staff behavior. The investment involved can be recouped in less than a year. Many types of equipment and computers generate harmonics within their line supply. The effects produced can sometimes be significant heat and vibration, potentially reducing the efficiency and service life of such equipment as capacitor banks used for power factor correction. Harmonic filtering is another typical passive energy saving measure to consider. As part of their drive towards synchronizing the consumption and production of electrical energy over the long term, energy distribution companies tailor their rates to encourage consumers to reduce their requirements during peak periods. Several different strategies are possible, depending on the consumption levels and operating requirements. Restricting demand, avoiding peak periods, load scheduling, or even generating additional energy on site. This is also known as demand response. What is demand restriction? Energy distribution companies can use this solution in supply contracts containing optional or emergency restrictive clauses whose application is determined by the consumer. This management policy is typically used during the hottest or coldest months of the year when companies and private customers have very high requirements for ventilation, air conditioning, and heating, and when electricity consumption exceeds normal demand considerably. Reducing consumption in this way can prove problematic in residential and service sector environments, as they may have considerably inconvenience building occupants. Customers from the industry may show more of an interest in this type of scheme and could benefit from contracts reducing unit cost by up to 30% if they have a high number of non-essential loads. Peak demand, peak demand avoidance. This method involves moving consumption peaks in line with the different rates available. The idea is to reduce bills, even if overall consumption remains the same. Load scheduling. This management strategy is an option for companies able to benefit from lower rates by scheduling consumption for all their processes where the time of day is neither critical. Additional energy generation on site. The use of generating sets to supply energy improves operational flexibility by providing the energy needed to continue normal operations during periods of peak or restricted demand. An automated control system can be configured to manage this energy production in line with needs and the rates applicable at any given time. When energy supplied from outside becomes more expensive than energy generated internally, the control system automatically switches between the two. No energy efficiency is possible without communication, but whether it relates to measurements, operating statuses, or rate bases, raw data can only be useful when converted into usable information and distributed on a need to know basis to all those involved in energy efficiency to improve the expertise of all participants in the energy management process. Data must also be explained as people can only develop the management and intervention skills integral to any effective energy saving policy if they fully understand the issue involved. Data distribution must produce actions, and these actions will have to continue if energy efficiency is to be sustained. However, this cycle of operations requires an effective communication network to be in place. The information system can then be used daily by the operators at the various locations where electricity is consumed to achieve the energy efficiency objectives specified by company management. It can also ensure these same locations make a positive contribution to company operations. Monitoring systems are for quick audits which can be performed on an ongoing basis, encouraging familiarity with data and distributing it can be help keep everything up to date. But electrical networks develop rapidly and are permanently raising questions about their ability to cope with such new developments. With this in mind, a system for monitoring the transfer and consumption of energy can provide all the information needed to carry out a full audit of the site, as well as electricity. This audit would cover water, air, gas, and steam. Measurements, comparative analysis, and standardized energy consumption data can be used to determine the efficiency of processes and industrial installations. For rapid, informed decision making, suitable action plans can be implemented. These include control and automation systems for lighting and buildings, variable speed drives, process automations, etc. Recording information on effective equipment use makes it possible to determine accurately the available capacity on the network or a transformer and to establish how and when maintenance work should be performed. Communication networks. Information and monitoring systems are synonymous with both Internet and Internet communication networks, with exchanges taking place within computer architectures designed on a user specific basis. For the most part, data exchange in the industrial sector uses web technologies permanently installed on the company communications network, typically an internet network, for the sole use of the operator. Concerning data exchange between components connected via a physical transmission link, the Modbus protocol is very widely used. Connection is possible with metering and protection devices in electrical networks. Initially created by Schneider Electric, it is very popular also in the building sector and considered as a standard protocol. For carrying large amounts of data between electrical distribution systems, the latest technology which is now introduced is Ethernet. It is strongly promoted for simplicity and performance. It is the most adapted media for either local display or distant servers. In practice, electrical data is recorded on industrial web servers installed in panel boards. The popular TCP/IP standard protocol is used for transmitting this data to reduce the ongoing maintenance costs associated with any computer network. This principle is well adapted to communicate data associated with promoting energy efficiency. No additional software is needed. A PC with an internet browser is all that is required. As such, all energy efficiency data is recorded and can be communicated in the usual manner via internet networks, GSM, GPRS, Wi-Fi, etc. For simplicity and consistency, measurement devices and communication interfaces are advantageously embedded in the distribution panel boards. Internet. Remote monitoring and control improve data availability and accessibility, whilst offering greater flexibility in terms of servicing. Figure K26 shows a diagram of this type of installation. Connection to a server and a standard web browser makes it much easier to use data and export it to Microsoft Excel spreadsheets to trace power curves in real time. Now, Ethernet technology allows easy connection of panel boards to the internet with compatibility with the rapidly developing smart grid facilities. In figure K26, you can see an example of an Internet Information Network protected by a server and monitored from the Internet network. Architectures. Historically, and for many years, monitoring and control systems were centralized and based on SCADA automation systems. These days, a distinction is made between the three architecture levels. Level 1 architecture, thanks to the new capabilities associated with web technology, recent times have witnessed the development of a new concept for intelligent equipment. This equipment can be used at the basic level within the range of monitoring systems, offering access to information on electricity throughout the site. Internet access can also be arranged for all services outside the site. Level 2 architecture. This system has been specifically designed for electricians and adapted to meet the demands of electrical networks. This architecture is based on a centralized monitoring system designed to satisfy all the monitoring requirements for the electrical network. As might be expected, installation and maintenance work requires less expertise than for level 3, since all the electrical distribution devices are already contained in a specialized library. In addition, acquisition costs can be kept to a minimum, as there are few requirements in terms of system integration. Level 3 architecture. Investment in this type of system is usually restricted to top-of-the-range facilities consuming large amounts of energy or using equipment that is highly sensitive to variations in energy quality and has high demands in terms of electricity availability. To ensure these high demands for availability are met, The system often requires responsibility to be taken for installation components as soon as the first fault occurs. This should be done transparently. Given the substantial front-end costs, the expertise required to implement the system correctly, and the update costs generated as the network develops, potential investors may be deterred, and they may require highly detailed prior analysis to be conducted. Level 2 and Level 3 architectures can be used side by side at certain sites. In figure K27, you can see a layout of a monitoring system. Smart panels are distribution switchboards which include the three key functions: measure, with embedded and standalone monitoring and control capabilities; connect, with integrated communication interfaces ready to connect the electrical distribution system to energy management platforms; and save, for example, to provide energy efficiency benefits through real-time monitoring and control and access to online services. With embedded metering devices, smart panels are the natural source of data with the electrical installation. Information can be made available on local display or sent via a communication network. Interface devices are implemented so that the communication is made simple and easy to install. The most advanced and efficient technologies used are Modbus, Modbus for transmission of information inside switchboards between components, Ethernet cable or Wi-Fi inside buildings, connecting switchboards with computers, and Ethernet on DSL-GPRS, connecting the electrical distribution system to online services. How smart panels contribute to energy efficiency? Smart panels are designed to monitor electricity in the installation right at the sources. This is the best way to know how energy is used. They are adapted to a large range of power, from final distribution up to the main distribution board. They offer large possibilities of visualization, from local to cloud-based integrated solution. They provide on-site real-time monitoring and control. The most essential information can be displayed locally. Control of switchgear is also possible. Key data and functions are provided on the local screen, on-site computer, remote control room, or cloud-hosted platform to detect demand peaks or abnormal energy usage, plan long-term energy usage, provide trends on energy consumption, making saving possible, and provide information for corrective, preventive, or predictive maintenance. Information is made available on PC for the site manager using web pages accessible with standard browsers. Access is also given to external experts for analysis and optimization. Systems for monitoring and energy control are physically very similar and overlap with the electrical distribution architecture whose layout they often replicate. The arrangements shown in figure K29 reflect the requirements typically associated with the distribution involved. They help to visualize and explain all the various services which can be used to promote energy efficiency. This diagram is an example of monitoring architecture for a small site with sub-metering and alarming on selected circuits using wireless power jack energy sensors. In this diagram, You can see an example of monitoring and control architecture for a company with several small sites. In addition, these diagrams make it clear that the choice of components is determined by the choice of architecture. The reverse can also happen, however, if a technical economic assessment of components installation costs and expected results show that the different architecture is more cost effective. In fact, the cost of these components, which sometimes have the same name but different characteristics, may vary widely and produce very variable results. A metering device can measure one or more parameters with or without using calculations. Replacing a standard circuit breaker with a circuit breaker containing an electronic control unit can provide a great deal of information on a digital bus. When designing these systems, therefore, it is very important to define objectives for energy efficiency and be familiar with other technology solutions, including their respective advantages, disadvantages, and any restrictions affecting their applications. To cover all the various scenarios, it may be necessary to search through various hardware catalogs or simply consult the manufacturer offering a wide range of electrical distribution equipment and information systems. Certain manufacturers, including Schneider Electric, offer advisory and research services to assist those looking to select and implement all these various pieces of equipment. How to evaluate energy savings? One of the main obstacles facing those interested in devising and implementing energy efficiency projects is the lack of reliable financial data to provide a convincing business case. The higher the investment, the greater the need for credible proof of the proposed advantages. As such, it is very important to have reliable methods for quantifying results when investing in energy efficiency. To cater to this need, the Efficiency Evaluation Organizations, the body responsible for evaluating performance, has published the International Performance Measurement and Verification Protocol. This guide describes the procedures used in measuring, calculating, and documenting the savings achieved as a result of various energy efficiency projects. So far, EVO has published 3 volumes of the IPM-BP, the first of which concepts and options for determining energy and water savings, outlines methods of varying cost and accuracy for establishing total savings made or those made solely in terms of energy efficiency. Before implementing the energy efficiency solution, a study based on IPM-BP principles should be carried out over a specific period to define the relationship that exists between energy use and operating conditions. During this period, reference values are defined by taking direct measurements or by simply studying the energy bills for the site. After implementation, this reference data is used to estimate the amount of energy referred to as adjusted baseline energy, which would have been consumed had the solution not been implemented. The energy saved is the difference between the adjusted baseline energy and the energy which was actually measured. If a, verification and measurement plan is put together as part of an IPMVP program, it needs to be accurate. Verification and measurement reports should be as accurate as possible for the budget available. The cost involved in verification and measurements should normally be comparatively low in terms of the anticipated savings. It needs to be complete. The study of energy savings should reflect the full impact of the project. It needs to be conservative. Where doubts exist in terms of results, verification and measurement procedures should underestimate the savings being considered. It needs to be consistent. The energy efficiency report should cover the following factors consistently: the various types of energy efficiency project, the various types of experts involved in each project, the various periods involved in each project, the energy efficiency project, and the new energy supply project. It needs to be relevant. Identifying savings must involve measuring performance parameters that are relevant or less well known, with estimates being made for less critical or more predictable parameters. And it needs to be transparent. All the measurements involved in the verification and measurement plan must be presented in a clear and detailed manner. Four study levels or options have been defined in line with the objectives assigned to this energy efficiency approach. Retrofitting isolation systems with measurements of all key parameters, which equals to option A. Retrofitting isolation systems with measurements of all parameters, that equals to option B. Whole facility, that equals to option C. And calibrated simulation, that equals to option B. Figure K34 sets out these options in a table. Figure K35 demonstrates the process for selecting an IP-MVP option for a project. Once the energy audit has been completed, the energy saving measures have been implemented, and the savings have been quantified, it is essential to follow the procedures below to ensure performance can be sustained over time. Performance tends to deteriorate if there is no continuous improvement cycle in place. A continuous improvement cycle will only work if there is an energy monitoring system in place, and this system is used effectively and maintained. The system supports a continuous and proactive analysis of energy use at the site and informs recommendations for improving the electrical distribution system. Support services, either on-site or at a remote location, are often required to ensure optimal performance for this type of system and the best use of the collected data. Thanks to their contribution in terms of experience and availability, these services also complement the operator's in-house services. The services available may include monitoring the performance of measuring devices, updating and adapting software, managing databases, and continuously adapting the monitoring system in line with changing control requirements. We come to the end of this presentation. Thanks for watching.